So to get neutrinos, even those very extreme energy neutrinos, to get them to interact enough to then get a detection out of that is very difficult. So nothing to fear. When I said the neutrinos are passing through us, it means that we are transparent to most low energy neutrinos. There is sort of a cross section of interaction of these neutrinos, and in certain energy regimes it's been shown, well, it was theorized and then probably shown that depending on the energy of the neutrino, you would get higher and higher cross section. So with the energy, your cross section would go up. And so then if you're below that sort of energy, for example, for these sun neutrinos, there is the cross section of interaction is extremely low, meaning that they don't really interact with anything along the way. It's kind of like if we could just pass through something as if it didn't exist, So that's what the neutrinos are doing. It's a very, it's difficult to intuitively understand because they're very tiny particles. They were thought to be almost massless, but they're not entirely massless. And depending on their energy, because they don't interact, it's almost like they're not there. You know what I mean? And that's why it's difficult to detect them, find them, etc. So anyway, okay. So this should give you significant relief because right now, as you read this, billions of neutrinos ejected into space by the sun are passing through your body and the earth as well as part of their lonely journey across the cosmos, through the cosmos. So lonely journey as in they don't interact with anybody. In the late 1930s, another particle called a muon, identical to an electron except that a muon is about 200 times heavier. So a muon is very much like the electron, but it's 200 times heavier. And as we shall see, they also have sort of a decay time that's much faster. And so you might not really meet too many muons in nature, in the wild either. But that too is a natural particle that can be made in certain processes and interactions. I've learned something new tonight. Thank you. Of course. Thank you for being here. So this muon, which is 200 times heavier than the electron, was discovered by physicists studying cosmic rays, which are showers of particles that bombard Earth from outer space. Because there was nothing in the cosmic order, no unsolved puzzle, no tailor-made niche that necessitated the muon's existence, the Nobel Prize-winning particle physicist Isidore Isaac Rabi greeted the discovery of the muon with a less than enthusiastic "Who ordered that?" Nevertheless, there it was, and more was to follow. So basically, they discovered a new type of particle, and some people were like, okay, so like, who ordered that? What does it give us? What does it mean? Is this anything special? Because it turns out that muons are just sort of a heavier version of an electron, as we shall see. I mean, I don't know if he tells us, let's see. Does he give us, I thought he might give us the decay time of a muon. I think it's only, if I remember correctly, it's around 2.2 microseconds or something, but please do verify that. I'm kind of searching my memory for the decay time of a muon. But basically, even if you make a muon, it's not like it will be stable forever. It decays. And so, in certain extreme situations, in these cosmic ray interactions, again, you might make a muon, but it is to be seen exactly how long it will remain stable as a stable particle, enough for us to recognize it as a particle. That's the question. So using ever more powerful technology, physicists have continued to slam bits of